Come back. Example 3. Find the volume of the solid obtained by rotating about the y-axis region under the curve y equals cube root of x from 0 to 8. So this is the region under the same curve y equals cube root of x. You want to take this region and rotate about the y-axis. Notice in the previous example, we took that region and rotated about the x-axis. You see? Now we want to rotate it about the y-axis. So what happens? You take that region and rotate it about the y-axis and you get solid space like that with a big hole inside like that. I hope you can visualize it. I take this piece and rotate it about the y-axis, this entire thing, yes, and I get a solid which has a hole in the middle. So it's almost like a cylinder except with a big hole in the middle. All right. So now notice this is rotated about the y-axis. So when I take slices, I get circular slices if I go across. If I cut across, so my cross sections are across the y-axis. So I'm going to go perpendicular across. And the slices have thickness delta y. You see, because it's vertical distance. So the thickness of each cross section is delta y. In other words, this entire solid is supported on the y-axis over the interval 0 to 2. How did I get 0 to 2? Well, height of the cylinder here is 0 and here is 2. So I'm looking at the y coordinate because that's on the y-axis 0 to 2. So that's the interval 0 to 2 and you take slices across. For each y here, when you take a slice, you get a cross section and when you cut it, notice there is an outer circle and an inner circle. You see, because of the big hole in the middle, there is an outer circle minus an inner circle. So the cross section is the region between two concentric circles. For each y from 0 to 2, the cross-sectional area is area of the outer circle minus area of the inner circle. Why do we do minus? Because you have to cut it out. So you see the inner circle has been chopped out. Outer circle has radius starting from here until here. That's the x coordinate. So outer circle has radius 8 and inner circle, that's the x coordinate. Horizontal distance is x coordinate. But x coordinate is y to the third because that's your curve. Y equals cube root of x. In other words, x is y to the third. So inner circle has radius x. Outer circle has radius 8. So area of the region between the two circles is pi 8 squared minus pi x squared. 8 squared is 64. So outer circle area is 64 pi minus inner circle. X is y to the third. X is y to the third squared. Y to the third squared is y to the sixth. So that's your cross-sectional area. Cross-sectional area is 64 pi minus pi y to the sixth power. So each cross-section for each y in the interval 0 to 2. So notice now you are taking integral 0 to 2 with respect to y of the cross-sectional area AY. Okay, so how did this come to be? Because now remember we are rotating about the y-axis. So you needed horizontal slices which made sure that our integration went from 0 to 2 with respect to y. All right. So now the rest is straightforward. Antiderivative of 64 pi is 64 pi y. Antiderivative of pi y to the 6th is pi y to the 7th over 7. Limits of integration are from 0 to 2. All I need to do is substitute 2. All right. 64 times 2 is 128 pi. 2 to the 7 is 128 pi over 7, you see. So all I need is common denominator. Assuming all my work is correct, that's your final answer. So notice the difference between this problem and the previous problem. In this problem, we went about the y-axis. In the previous problem, we went about the x-axis. All right. And that gave us different answers, of course. All right. Now here is another related problem. I'm looking at the same curve, but instead of this time looking under the curve, I am looking at the region bounded by the curve and y equals to that height and the y-axis. So that's your curve and that's your line y equals to, and that's your y-axis. So I'm going to take the region in between these three boundaries and I'm going to rotate that about y-axis. When I rotate that, you see, that is the solid I get. I took this region and rotated it about the y-axis and I got this particular funny cone-shaped, funnel-shaped solid. Find the volume of this solid. So now if I take, again notice, I have to take horizontal slices. If I take vertical slices, I'm not doing anything useful, you see. I take horizontal slices. Why do I take horizontal slices? Because my curve has been rotated about the y-axis. So notice this curve, the solid, is again supported on the y-axis from 0 to 2. And the approximating cylinder has width delta y and was the radius of each of these. Radius is the x coordinate. You see, going from here to here, I get x coordinate. X coordinate is y to the power 3, just as in the previous problem. In the previous problem, we had an outer circle. Now we don't. All we have the inner circle. So this volume is integral 0 to 2 of the cross-sectional area pi x power 2, that is pi y cubed power 2, right? X is y cubed. So that's y to the power 6. Antiderivative is y to the power 7 over 7. 0 to 2 are the limits. Substituting, you get 128 pi over 7 cube units. All right. So from one curve, we got three different volumes. One rotating about the x-axis. Another, you take the region below, rotate it about the y-axis. And the third, you look at the region above, rotate it about the y-axis. Indeed, you could also have taken this and rotated about x-axis. That will be an exercise for you to try, okay? By now you have enough ideas. So, next problem, we'll try some other curves. I'll come to that in our next video. Until then, bye.